Computer. Great. Welcome to Deep Learning for NLP Lecture 4. And today's title is Text Classification 2, and we're finally coming to deep neural networks. Great, but we actually didn't really finish last time as I thought we would finish on time. So let's call it a, well, I think, oh, let me just get it over here. Get away. We didn't finish the full lecture, which was basically a glitch in the screenplay, kind of, because I thought we should pack everything into one lecture. But I guess the discussion about back-off words and subword units and so on was kind of crucial, and I'm glad we spent a lot of time on that. So let's finish today what we didn't finish last week, and then move on. Okay. So where did we finish last time? Okay, so what did we do? We did some, what was that? Binary sentiment classification, right? So we had reviews or something like that, and we tried to build a classifier for whether it's positive or negative. So how did we map the labels, like positive or negative? Anyone remembers from last week? What did we do? So we had positive and negative, but we need numbers because we're working with functions. So how did we map them? Yes?
You mean the logistic regression?
Well, the got labels in the first place. We had a logistic regression, which was part of the model, but what did you do with labels like positive, negative?
It's 1 and 0.
Yeah, 1 and 0, exactly. So 0 for negative, 1 for positive, arbitrary decision. This is great. And we're representing the input text as something. There's a term for that. Anyone remembers the beautiful word? Yes? It's a back of words, or the average back of words, exactly. And we use some sort of functions to map the back of words into the 0 and 1, which we want to predict. So what was the function? Anyone remembers what the function was? It has a special name and special properties. Yes. We had a sigmoid function at the end of this complex function, not complex, complicated function. We had a sigmoid to put everything into 0 and 1, but the main kind of building block of that was we didn't have activation functions really yet, I guess. We were doing something from linear algebra a little bit. So what was that?
Gradient descent.
We didn't touch gradient descent at all last time. Sorry. I don't remember actually if we touched that. We will touch it today, yes. We did, yeah, the threshold function was kind of sigmoid function. Like sigmoid is mapping anything from infinity to these two. Yes. Yeah, we had this linear transformation, exactly. So the core was the linear transformation or projection, linear projection. Yes, come in. We have, again, premium seats in the first row, last row. So it was the linear transformation, exactly. It was the main building block for taking the back of words or the vector and map it to some low dimensional space. Okay, so the linear function and then followed by the sigmoid function to map an arbitrary range from -infinity to +infinity into numbers between 0 and 1. Okay, so here's the thing again. So we had this, the x was the vector of these back of words, and we had this weight vector basically in this case, and this is the bias, and we squeeze it through the sigmoid function and get the final prediction, which is a number between 0 and 1, right? And we also had this. You have a question, or no, you don't have a question. Okay, sorry. Yeah, no worries. And excuse me. And this is the computational graph of this function. So what it means is that the x is the input, and this is basically constant here because we don't want to do anything about it. I mean, this is given, right? We have the text is given, we extract the back of words, and we can't change it. What we want to change are these parameters w and b, which we want to make as such that what's coming out of here is doing what we want it to do. So for texts that are kind of negative, it gives us zeros, and for texts which are positives, it will give us the ones. And here we have this function that this is the linear mapping. So okay, sanity check. So we're mapping from large dimension to small dimension. What is the input dimension of this function? What is the input dimension of this x? Sorry, what is this x dimensionality? What is it again? So we have back of words. What is the dimension?
1 by the length of the vocabulary?
It's basically the length of the vocabulary, exactly. So this would be the size of our vocabulary, exactly. It's a vector, so it's not 1 times. I mean, we don't have to make it matrix. We don't have to make it complicated. It's just a vector, a bunch of numbers. Then, and what is the output of that again? What is the output of this sigmoid? What's the dimensionality of that? Exactly, it's a scalar. It's 1 dimension. It's a scalar. Okay, so we're basically mapping from super high dimensional space. Size vocabulary size could be, I don't know, 100,000, for instance, into 1 dimension. And in this 1 dimension, we squeeze it through the sigmoid function to get the decision rule. Okay, this is all good. And I guess we had this decision rule as well last time. So basically, we're saying what comes through the sigmoid, if it's larger than 0.5, the result, we say, I mean, we're basically rounding. So if it's bigger than 0.5, it's positive, or the prediction is not 1, and if it's smaller than 0.5, it's 0. And then we have this nice interpretation, which gives us basically the conditional probability. So we can interpret this as a probability of being prediction 1 given X. Yes, you have a question.
Like probability of sigmoid of f of X equals probability.
No. So the sigmoid of f of X is exactly the probability of the prediction being 1 given the features. I'm almost 100% sure this is it. Like, this is a value, right? I mean, this is something in between 0 and 1, right? The output of that function. Let's call it, we have y, so let's call it z. So z is a number, and then it corresponds to this. Is it clear now? Cool, yeah, thanks. Yeah, I had a typo on this slide last week anyway. Okay, good. So far so good. Everybody's with me. Any questions so far? This is great. So we have a linear model where we have a linear model plus some nonlinearity, and we want to find the parameters. So we want to find the best parameters, which kind of give us what we want to do, like predicting given a new vector or a new text. When we tokenize it and do the back of words thing, we want to predict what is the classified into negative or positive. And how can we tell the model what's, are you doing well or are you doing not well? On these training examples, we introduce the loss function. So it's a crucial concept in machine learning and deep learning is the loss function. So basically it's saying how much, so it's quantifying, it's saying how much loss is suffered. Well, it's not a suffering, basically how much loss we obtain when predicting this prediction y hat, while the true label is y for a single example, right? So basically, if we have a binary classification, the loss function, which is parameterized by this y hat, which is the prediction, and y is the gold standard data or data point, it's from a tuple of these two into real numbers. So the loss is basically gives us a real number, and the loss should have some properties. Namely, the smaller the loss, the better the closer the predictions should be together. So it should be like positive number. It should be maybe, well, it doesn't have to be positive, but at least it should have a minimum. And when the minimum is hit for these two things, this should be the correct prediction, right? So if, for example, y is 1 and y hat is 0.999, the loss should be very low, right? Because they are very close to each other. So any questions so far to the loss? Like what are we trying to achieve with that? We're trying to basically make it as small as possible for one example. So which means then, giving labeled training set. So now this is about like one single example, but we have a training set, which is a sequence of n training examples with x and y. So the input, so to say, features and the labels. And we have this notion of loss per instance and parameterized function fx. So what is our parameterized function fx again? Oh, parameterized functions looks terrible. What is it again? This is our linear function and the sigmoid. So this is the function we're mapping, the input to the output. We define then the corpus y loss. So it's basically for all training data with respect to the parameters, theta is the average loss over all training examples. what does it really mean is that it's very simple at the end. We iterate through all the examples in the training data. So we have n training examples and we iterate through all of them. And for each of them, we compute this per instance loss, right? So basically what is here is the prediction, so y hat, and this is the GOT label for this ith example, and we compute a loss, right? As in the previous, what I shown, like 0, 1 and 0.999 would be like, per example, loss. And then we just sum them together for all the training data and take the average. Yeah, so this is the average loss per corpus. Any questions? Okay, this is great. So we have a loss, and we say the smaller the loss, the better we kind of mimic the gold standard labels. So does it ring a bell? What should we do? Why do we care about the loss, actually? Why is it important? Why do we need to have some function as a loss over the training data? We can minimize it. Exactly. We want to minimize the loss. We want to make the loss as small as possible on the training data. Okay, this is a great question. So we want to minimize a function. Does it ring a bell now? Can we minimize a function? We can use the gradient descent to minimize the function. This is great. Okay, cool. Wow. We talked about a lot of functions, and last week we talked about like all the linear functions, what they have to, what the properties all the functions must have in order to be kind of minimizable, the way we know with the gradient descent. So all the functions must be or continuous, yes, which kind of is a different term for being differentiable. They don't have to be continuous because you can make exceptions, but they have to have derivatives with respect to everything what's coming in. Because if we know the derivatives, we can compute what? The gradient using the very famous technique of the backpropagation, the chain rule, the backpropagation, exactly. And now we say, oh, okay, so I can actually use backpropagation to compute gradient over all my training instances, and through doing this, I will minimize my loss function. Wow, this is great. This is machine learning. Basically, this is it. This is deep learning. One thing we need to talk about, like, what is this loss function, right? Yeah, what is it? This is very abstract. Like, what is DL? I have no idea. We'll talk about it later on, like typical examples of the loss functions. But so far, so good. So we can take the loss function and take training as optimization. So this is the loss. Very fancy L here of the theta, very fancy terms for parameters. I mean, so the question here is like, is it okay like so many mathematical terms or not? I mean, do you like it? Do you hate it? Or it's fine? Who hates it? Who hates like slides in LaTeX with mathematics? That's fine. I mean, raise your hand. That's fine. I'm really curious. I like to write it. I like the way, it looks in LaTeX actually. So I like writing it. It's really like, I do research for writing papers in LaTeX. Okay, I shouldn't put it on record on YouTube, but it's true. Okay, so I mean, you can describe it in many different ways, but the mathematical formulation is kind of, it could be precise most of the times, but we're misusing notations here. But anyway, so everybody's fine with that? Everybody understands what we're talking about? I'm trying to take it as, also explaining like what all these things are. Okay, good. So we have this loss for the training data set with n examples, and the training examples are fixed. So this xy are given and the yi's are also given. And we want to set the values of the parameters. So no matter what it is, it would be typically the w's and b's, such that the value is minimized. So the final formal kind of definition of this minimization would be, we want to find such parameters with this tiny hat. So the hat is like, it's not the truth, but sort of almost. We're trying to predict as the minimum of these parameters. So where this complicated function, this is a complicated function, right? This is a really complicated function actually, because it's an average of a sum of a loss of, here will be a linear transformation through sigmoid. So it's kind of complicated function, but we can still work with that easily. And we want to find such parameters, such theta, that this function will be at a minimum. Whether it's global minimum or local minimum, it's a question. Typically, global minimum is great because then we really know we're at global minimum. If we have the function, if they are, how do we call it? If they're like fully convex, you can find, so it's like a bowl, you can go to the minimum with stochastic gradient descent, but deep learning or deep networks are not really such. So they're kind of very nested functions, and you will mostly reach local optima, but this is good as well. So this is what we're trying to achieve. So we want to minimize the function, okay? And we use the techniques we know already. This is great. So now coming to the question, like, what is this loss? What is this thing? So let us show a simple loss called the logistic loss, or also binary cross-entropy. And this is something you should know, okay? Even like the formula you should kind of know, because this is so central to many things. It looks complicated, but it's not, because we will show later. It's coming from actually a concept from probability theory, from KL divergence between two distributions, and it's just one kind of incarnation of that for the binary task, right? So we're taking so these y's. Okay, sanity check. What is this y? What is this? The true label. Thank you. What is this y hat? Yes, again. Say again? The predicted label, exactly. This is what's coming from the network. Okay, so this is logistic loss, and in order to optimize this function, we need to have, again, one thing. Every function which we plug into the complex functions, the complicated functions, we need one thing to work with that, with stochastic gradient descent. What do we need? This is a nice function, but it's not complete for us, because I mean, if I tell you like implement it in your network, you're missing one part. What do we need? We need a derivative, exactly. So what is the derivative of this function with respect to the y? No, y hat. I'm sorry, y hat. This is the input, because this is constant. So what is the derivative of that? I don't know. I look it up, to be honest. I was too lazy to kind of compute by hand. But at the end of the day, it's because of all these logarithms, so it's kind of nice. It's basically this kind of fraction. So you don't have to remember this derivative. I mean, you can, if you're stranded on a desert island, you would end up with, you would come up with this derivation if you really have to, I don't know, build a neural network there by your own model. So I'm just saying, like, well, it's not, it's a nice function. Like, the derivative is not really complicated. Okay, so we have the derivative of this logistic loss. Great. So now, coming from the computational graph we had so far, now we have the full computational graph. So again, this is the inputs. This is the parameters, W and B, so the weights and the bias, and then we have this linear function. What is this sigma again? Yes? The sigmoid, the sigmoid. Okay, good. It's a good hint, exactly. So it's a sigmoid, and then we have this loss function, and the loss is taking the prediction from this function, and taking also the gold standard label, right? So, and now I already kind of revealed the secret here. How can we minimize this function? Okay, any question to this computational graph? Is it clear for everybody? It's very simple, I would say, but it can get, it's a building block of I would say, like, deep learning. So if you see like a neural network, you would see something like a graph, but in very many different flavors. So I'm using this kind of very simplistic function-oriented graph, but I guess it's clear. Any questions? Good. So we minimize this function by gradient descent and backpropagation, right? So, and now we're coming to a very famous kind of algorithm for training these models. Although this is not, this is still not like a deep learning model. It's like one layer binary predictor, so logistic regression in a way. But we're gonna use this stochastic gradient descent, so online stochastic gradient descent. Okay, so this is something which looks maybe a little bit complicated, but let's have a look. So what do we need for this function, for this stochastic gradient descent? Again, we need the function which takes the input and the parameters and produces the output. Well, what is this? This is the training data, right? So we have n examples and n labels, and we have this L. This is the loss function. Loss function. Okay. So, and then we're gonna do with, as in the standard kind of minimization we had with just simple functions, not these complicated graphs. We're gonna continue while we're still going lower and lower. So maybe number of steps, or just we don't, we hit some local minima and we stop. So some stopping criteria are there. What we're gonna do is we sample a training example from the training data. So we just randomly choose one. And then we're gonna compute the loss on this example. So what is this loss computing? What is the output again of this loss? It's gonna give us a number. Loss is giving us a number. It's a number, right? Should be positive, real number. And then having this computed this number, this loss, we're take our computational graph and compute the gradient of this loss function with respect to all these parameters. Okay. What does it mean exactly? Let me come here. So we run this sort of forward pass where we compute a loss. So we have this loss. So everything is computed. We know all these values of all these nodes, right? This is very similar to what we did, with the computational graph in the second lecture. Looks maybe more complicated, but it's the same, conceptually the very same thing. So we compute all these outputs, and then we're gonna start from here and ask, okay, what is the gradient of L with respect to L? Is 1. So this is how we start, and then we're gonna come back. What is the gradient of L with respect to sigma? Okay, L with respect to sigma, and what is the gradient, and so on, and we end up here. When we do this backpropagation, basically, we end up here with what is the gradient of L with respect to B, and here we'll end up with what is the gradient, partial derivative, the gradient of partial derivative is the same thing, of L with respect to this vector, so each of these things, right? And this is what we want. We want to find the partial derivatives or the gradient with respect to these things. We don't care about the input, this is constant, right? We don't change the input, obviously. We only care about the trained parameters here. So the forward pass is shown here. We compute a loss, and by computing the loss, we compute all the outputs intermediately, and we store them in the nodes. And then for the backpropagation, we're going to reuse them for computing the gradient. So once we get the gradient, which is basically a vector of partial derivatives, so this gradient is kind of nothing else than to B, and then awful. This partial derivative with respect to W1 and W2 and so on. So these are the parameters we need. All these are all the dimensions we have, right? So we're in highly dimensional space, and now we're going to take a step in the opposite direction of this gradient. So this gradient, this is how we how we denote them, but in reality, this will be numbers, right? This will be a vector of real numbers. And the gradient size, so the gradient is nabla, right? So the gradient size is the number of these W parameters plus 1, which is the bias, right? So this is the size of the gradient. And this is the multidimensional space of the parameters when we are moving ourselves. Once we compute this gradient, we take this eta. Is it eta? Yes, I guess so. Eta, which is what is the eta again? What is this thing we're multiplying the gradient? The learning rate, exactly, the learning rate. Thank you. We multiply the gradient, which is a bunch of real numbers, and we moved the parameters, which is again a bunch of numbers, somewhere else, where we get smaller loss, and repeat until we can't do anymore. Okay, so I'll let you kind of digest it, and if you have any questions. Great, any questions? Yes.
What does ongoing mean?
Online. Okay, this is a great question. Thank you. Any other questions before I answer online? So everybody is happy with it? Yes.
Why is it in the form of the vector?
Oh, yes. So why is it in the form of the vector? It's just a bunch of numbers. It doesn't matter. So it's the gradients. I mean, if you look at it like that, they are kind of separated because here you have, oh, you don't see, okay, sorry. Like that. You have so this is a matrix, this is a number somewhere in your code somewhere. This is a vector. This W is a vector. Because you're multiplying vector by vector, a dot product and plus B, right? So these are somewhere, right? But in fact, like from the mathematical perspective, you're minimizing a function in dimensions which corresponds to the number of the parameters. Because if you minimize like one-dimensional functions as we did before, you minimize in just one, basically, one direction. You find it. If you have like, what is it? The banana function was 2 dimensions, and you find the minimum in 2 dimensions. Here you have W plus 1 dimensions, and in that you're finding the minimum. You're finding the spot of these parameters where the loss will be minimal. So it's kind of large number of parameters, and you can see it as a vector in this high-dimensional space. At the end of the day, it's just a bunch of numbers. Okay. Yes. What is the shape? It's very awful one. So the point is, it's hard to visualize first because you have like you rarely have 2 parameters. This could be, well, how much parameters you need if you have like vocabulary of 10,000 words. So how many parameters you will train here? 10,001. Yes, take 100. Okay, so we have like, let's take like 101 dimensions. No. That's so what you're plugging here is a back of words, and the dimension of the back of words is the size of the vocabulary, which could be even if it's 100. Okay, let's say it's 100. So V is 100. If you multiply this with another vector, this vector dimension has to be 100 as well, right? And this is plus 1. So you have like 101 dimensions to optimize. Right? So you are in a 101 dimensional space, finding a place in this 101 dimensional space where you have minimum of some loss. It's easy to visualize if you had like 2 parameters. So you have like 1 word and 1 bias. Yeah, so you have like 2 dimensions, and you see like maybe the banana function, whatever. So you can visualize it, but there's no way how to visualize 101 dimensions, right? How does it look? So some people try actually looking into that, how the surface would look if you project it down to fewer dimensions, and it's not a nice surface. It's kind of very bumpy, and there's a lot of saddles. Like everybody knows what a saddle is in 2 dimensions. It's basic. I don't have a picture here. So if you have like mountains here, and here's go down like a saddle in the mountains. Yeah, if you go, if anyone's hiking in the mountains, who's hiking in the mountains, right? Okay, so you go up, you go to the saddle. And you have 2 peaks on the sides, and you just cross the saddle to the next valley. So you had a saddle, and typically also these functions, or in deep neural nets, when you find a minimum, it's not really like in the valley, the minimum, it's typically some saddle point where you have 0 gradient because it's kind of flat on the saddle, but it's not like optimal because you can still go down. Sorry, I didn't get a question. How so? Well, you know that you minimize the loss, and your function with these parameters will give you the best prediction for your training data, and at the same time, it will give you like best prediction for your test data if they come from the same distribution. Does it make sense? Okay, if we can take it offline, but any other questions before I hit what's online? Let me come here. Okay, it's not the case. If so, just we can talk about a lecture. It's online because here on the line 4, we're taking a single training example. right? We're picking random example from the training data, and it gives us only a rough estimate of the corpus loss, because we're trying to minimize the corpus loss for the all training data, but we just pick one single training example at a time. That's why it's online, because you can proceed, take one example, compute a gradient, do the step, pick another example, and so on. So it could be used when your data is actually coming online from, somebody's just sending you a new label data. You pick one at a time and learn new kind of set of parameters. Okay, good. Is it a good thing or a bad thing? I mean, what's the advantage or disadvantage of having this online thing? What could be the advantage?
Quick update.
Yeah, quick update. Yes, quick updates. Basically, you can basically streaming data. If you have any streaming data, so you can update on the streaming. Okay. Any disadvantages of that?
I think it will take longer than if you use the instead of the
Exactly. So mini batch is the keyword, right? So you heard about mini batches is great. Yeah, it will take a lot of time. Just do this backpropagation after every example you see, because it's kind of complicated computation. I mean, complicated. It's just a lot of computations, and maybe there's a better way. And also, the point is, you're taking a single training example, and this example could be kind of bad and gives you like a wrong direction in the gradient, right? Because you want to, you want to go to the minimum in this high dimensional space. And this particular example is kind of misleading you somewhere else because it's just bad or somehow like out of distribution, whatever. And that's maybe not what you want. So instead, you can do better estimation of this corpus loss. And you're going to use something called, right? You can use mini-batch stochastic gradients. And so this is the algorithm for training neural nets. Mini-batch. So how does it work? We have the same kind of setup. So we have the same neural network, the function, the training data here, and the loss. And again, we iterate while something. And then we're not picking just one example, one training example, but we're picking n examples at a time. Where m could be, something between 1. If we had m1, then we're back to the online gradient descent. If m is more than 1, then we have this batch. So mini batch, it's a batch sort of, or if it's small, we call it mini batch for some reasons, I don't know. And what you're gonna do here is that you compute the loss for each example in the mini batch, as we did before, and then you're gonna basically make the average gradient. So you're basically, for each example, you take you divide it by the number of samples in the mini batch, but at the end of the day, what this thing is doing is that we're getting the g hat is the average of the gradients for each example in the mini batch. Okay. Yes.
So after the loop is done,
g hat. Yes, this is LaTeX. It's like hat g. It's gonna be what? So exactly, this will be the average of the gradients for each example in the mini batch.
Okay. So why are we dividing?
Why is this here? Yeah, because it's right. It's a great question. Because it's gonna be, what we really want to do is to kind of, if you program it naively, you would collect the gradient vector for each of these examples in the mini batch, right? You get gradient 1, gradient 2, and so on. And then you would do the average, like sum them up and divide by number of them. Yeah. If you do that, you need m times more space to store the gradients, right? Because you need, you need a gradient for the first example. It's a vector of numbers. You need a gradient for the first example here, for the second, for the third, for the fourth, up to m.
Why?
All right, you can sum. Yeah, that's correct. Sorry, you can sum them together and divide by n. Yeah, that's the same thing. Okay, yeah, you can do that. I mean, this is basically doing it in line. Yeah, I got you. No, I don't think so. I think it's just a design decision. Like, it's maybe faster just to divide them and sum them together. But you can do it afterwards. Yeah. Sorry.
Is it summing up first and then dividing faster than dividing
I think it depends on the implementation. I don't know. I think, I mean, they are mathematically it's the same thing. Okay. There might be differences somewhere. Yes, you are saying.
Why is the mini batch thing faster? You still have to take computate the gradient for each of the...
This is a great question. So why is the mini-batch gradient faster than just doing before? Because at the end of the day, you have to go through the computation loss and gradient for each example anyway. I do have an answer for that. I'll come to that later. Any other question? You were something you were asking as well? The same. Thank you for spoiling that. Okay, yes. Okay, good. So I'm going to address this. Any other question to the mini-batch stochastic gradient? Yes.
Which one did it go?
Because your stochastic means you're randomly sampling the batch. Right? This is it. I mean, here it's stochastic because you're sampling, you choose randomly one example from the training data. Here you're sampling a batch of training data.
Does not have to do all the training data.
No, and it's a parameter. Yes, exactly. I'll come to that on the next slide as well. So we have two questions. Any other question? Which is yes. The starting weights. Where do you start? What is our parameters? Okay, so how would you set up your parameters? What is the W? So you start from scratch. What is the W's and what is the B's? So I would say the good default could be all zeros. Will it work? Actually, I thought about it in the car now, and I think it will work. It won't break. I think it will work, but just the first iteration will give you like zero inform. I mean, after the first kind of stochastic gradient step, you will end up something somewhere else. I mean, there is no local minimum maximum in the zero parameters. It's just a point, right? But typically, what we do. So I need to double check. I was really thinking about it, like whether I shouldn't put it to zero, but then why not? Typically, we sample them randomly. Random, and there is some kind of from which distribution uniform between something and something. So you initialize randomly the weights of your model. Okay, so random could be, but I think like zeros could be also fine. Maybe like you have zero multiplications, which gives you a little bit little information than having some random numbers. So it's maybe better to start somewhere else. But I don't think it will break with zeros. I have to double check though. And yes. I don't think so. I don't. Why should be there like a zero gradient? Yeah, exactly. I mean, exactly. I was sitting in cars like, yeah. I mean, there will be like zero gradients. No. Why should there be a zero gradient? Because you compute the loss and the gradient. I mean, show me the proof. I mean, maybe I'm wrong. So I would need a piece of paper as well for this. Anyway, any other question? Before we move to these two questions, like what is M and why is it faster or better? Okay, let's move on. So the mini-batch size can be something between 1 and the full data set, right? But typically, what's the driving factor of the batch size? Sorry, I have a new phone and I can't turn it off. Come on. Sorry about it. What kind of drives your mini-batch size? What do you think? What do you? Okay, let's address the second question first, because this can be easily parallelized, right? If you look back, this kind of two things are running for each example, but these examples are independent, and also you don't change anything in your parameters yet, so you can just run it on different kind of cores, whatever. So you can parallelize that. If you do it very cleverly, then on GPUs it gives you like super boost. Okay.
When you also parallelize the online thing, if you just run single examples on different cores?
I think here well, the only thing you can really parallelize here is maybe some matrix multiplication, in the network. But itself, like naively, you have just one function running, and this is one function, so there's nothing like globally parallelizable. Well, here you can really say, oh, this example goes here, this example goes here, and you can compute them like parallel. Okay. So, and the higher values of n, like this, the size of mini batch. So the high values give you better estimates. Smaller values like more updates and turning faster. There is one thing actually in reality where you need to pay attention while choosing m. What is it? Anyone knows what's the limiting factor of having smaller batch sizes than the full training data set? If you run this in parallel, let's say you parallelized everything here, and you want to run it with n as large as possible. Memory, yes, you're running out of memory. So if your network is big and you're running on a poor guy's A100 NVIDIA GPU with 80 gigs RAM, and you're running a large model, then your batch size will be 16, 32, 64 maximum. Because the network is just, I mean, with billion parameters, you need to fit it in memory. And in a batch, if you run it in parallel, you need like as much memory as your batch size. So this is the factor slowing down. Yes.
Slight noise is also good for building up several points other than that.
It gives you, so like getting rid of saddle points. I don't know. I mean, I don't know. I don't think there's a general kind of a rule of thumb, but it gives you better estimate of the gradient. So because you're kind of averaging all the gradients for all the different points, so then you know much better where to go for the better loss. But if it's just a saddle point or not, I don't know. Maybe there's some theory about it, but I don't know that. I'm sorry. Okay, any other question? Great. So we can build this thing, right? I mean, we have computational graphs. We have backpropagation. All these functions in there are differentiable. You can plug them together. You can run backpropagation, and you can run stochastic gradient descent. So basically, nothing prevents you now from building this thing from scratch, if you want. Okay. Now, we are talking about, so far, we are talking about binary classification, okay, which was like, yeah, 0 and 1. But typically, the world is not binary, or classification tasks in NLP are not binary at all. And we want to classify maybe into distinct categorical classes. So, for example, let's try a task of language identification. So the input will be again back of words or back of subwords, whatever. Maybe subwords are better, but let's take it as back of words. And the output will be, I want to tell whether the document is in English, French, German, Italian, Spanish, or other. So we have 6 classes now. It's a very simplified version, but why not? For some cases, it might be good. And we want to classify it into these categories. And the thing is, there is no ordering of these. So there's nothing saying like English should be higher than French or whatever. There is nothing. There's different categories. So how do you gonna encode this? I mean, in the binary we had negative, positive, 0 and 1. But now how are we gonna encode this into something, into maybe, I don't know, a number, a vector? Any ideas? How can we work with this categorical data? Yes.
So just have a 6-dimensional vector as output instead of 0 and 1.
We will have a 6-dimensional output vector with 0s and 1. Okay, cool. Does it ring a bell for everybody here? Because we had it already. It's a similar to, it's one-hot encoding. Exactly. We had the same thing for words. Words didn't have any ordering, and we just put them into like 60,000 big vector, and there was just 1, and everything else was 0. We're gonna do the same thing with the labels here. So one-hot encoding, exactly. And we're gonna arbitrarily say, okay, this is going to be like 1 and 5 zeros, and French gonna be on 2nd position, and so on. And the dimensionality of this y vector is now the number of classes, right? Any questions? Why we're doing this mapping, one-hot mapping of the label? Yes.
Couldn't we also, instead of 1s and 0s, use confidence for every language and see which is the highest?
But this is the gold standard labels. We know. I mean, this is like how you present the task.
Oh, right.
We're saying, yeah, this is in German. So, but theoretically, you're right. You can put the probability distribution over these categories and say, yeah, maybe this is like 80% German and 20% English, if it suits your use case. But this is like very simple, and you're classifying. It's like hard classification. You're saying, yeah, either or the other. We're not talking about like language switching, and stuff like that. So any other question? This should be. I hope this is clear. Like this is the same thing as we did with words. One-hot encoding of the labels. Yes.
With this specifically, there should be texts that are exactly the same in English and in German because the same words are used, but it's the short enough text.
Yeah. So if there's okay, this is a tricky question. So if I really want to classify text into languages, and there are two documents that are exactly the same in English and in German, then something is wrong with the text, or something is wrong with my data set, or something is wrong conceptually with my task. So I'm not expecting that, but obviously there could be case. What's the case?
For example, Google Translate has auto-detect language, and if I put the and DI here in, could be die in English or the article.
Sure, yes, of course, but you're translating words, which is harder.
They can also translate like sentence strings.
Yes, yeah, okay, sure. I mean, this is not easy task, right? And language identification is not easy, although you think it's easy. So there's the research on that, and you have like corner cases where, yeah, it will break because you have the same label for the same, so different labels for the same inputs. Yeah, so you have to take it as a feature of your data set and kind of live with that, right? Okay, good. Any other question which is not that tricky? Yes.
Would it be possible to just use a vector with 3 entries and then count up in binary, like the end was 1?
Okay, good. So yes, so you would be basically mapping that to binary numbers,
yeah.
Right? But you're imposing them then some sort of ordering or similarity, because some numbers are close to each other than the others. But these are like distinct things, and the Hamming distance should be the same for all of them, because we want to map them as farther as possible in this space. Okay?
Yeah.
Good. Let's move on. So how can we solve this? Okay, so we know we have linear functions, we have the sigmoid thing, but now we're not classifying into binary, into 0, 1, 1. We are classifying into a vector. So how can we solve this? So I have a possible solution here. And we can actually have for each of these languages, so this fancy L here, for each of them, we can have a separate weight vector. So for example, the weights for French, and we can have the bias scalar here for each language. And then we can just basically do the same thing as we did before for the binary prediction, and take the input vector, multiply that for with the particle language weights and bias, and then pick the highest scoring language. So it would be like the maximum argument from all of these 6 ones that gives us the highest score for this computation. Does it make sense? So basically we would say, well, we're not saying there's only 2 languages and cast it binary, but we would say like there's 6 languages and each of them has a set of parameters. And the equation we're using here would be the same. So basically, projection of the input times the parameters for the language and the bias. Okay, this is great. So we can basically take these and rearrange them into rearrange these vectors into columns of the matrix W, which will be then we'll have number of rows, which is the input dimension, and 6 columns, and we would get again linear projection. Oh, this is kind of cool, right? So we're cramming everything from separated languages into one matrix, and it's doing the same thing. It's a projection from a vector into another vector. So this would be like the result here would have dimensionality of 6, because we have 6 languages. Any questions? Yes. What do we do with biases? Well, we treat them the same way as we did before. So we have, for each language, we would have basically, oh, here, what do we do with the biases? Yes, so we convert the bias into also like a 6-dimensional vector. So everything will kind of work with the dimensions here. Yeah, thank you. Any other question? Yes.
So if I understand it correctly, we have this forward for every language.
Exactly.
In that case, could it also be that for all the weights, it just says, oh, the probability is really low, or for multiple it says the probability is really high.
Yes, I know. So we're not gonna. You're talking about putting the sigmoid over that. I mean, the sigmoid tells you probability of whether it's the The linear mapping is basically a projection into a number. So now for each language, you're projecting the input to a number, and it tells us some sort of affinity, or how for this language, this input kind of what values is giving us. But we're not saying the probability at all. It's just numbers, because if we do this, the output will be a vector of size 6 of real numbers. But these could be from minus infinity. Oh, sorry, it's not infinity. This is infinity to plus infinity, because we don't put any constraints here. So it just gives us it's a projection to low dimensional space, nothing more. There's no probabilities. Okay, does it answer your question? Okay. Any other question? Yes.
And then do you take the highest one, or?
Yes, I would take the highest one. Yeah, I would take like which one is the highest. This will be the language.
Okay.
Why not? I mean, we can do that. Is it a good thing to do? Yeah, maybe there's something better. But theoretically, we can just make this projection and take the maximum here. And we can learn the weights in a way that it will just work out nicely. Okay? Yes.
Can we, instead of doing this, like having specific, it's almost a different model for each language, right?
Mm-hmm. Yes, exactly. So can you have like different models for each of language? Because if you look at this like that, then it feels like different models for each language. If we cram them to one matrix, it's still the same thing. They are independent, because these are kind of independent. We're gonna use something which make them kind of dependent, and really we'll try to pick one which will be the answer and kind of suppress the others. We'll get to there. We'll make it everything fit together, okay? Yeah, linear regression, but you would then, so linear.
Like if the prediction was from 1 to 0.8.
I know what you mean, yes. I mean, conceptually, you could do that, but then you impose an ordering on your categories because you're mapping them to real numbers. And this is what we don't want to do. I mean, I think you could do that, but then you're putting meaning on things which don't have meaning. You're putting ordering of values to languages, while here just one hot. I mean, they're just, discrete, completely independent, okay? Good, let's move on. So what we're doing is that projecting input vector to the output vector. So the dimension in was what was that? The vocabulary size, right? So one hot encoding of back of words. And the out is the number of classes now. So recall from the last lecture that we doing this, basically, we talked about it already with this high dimensional linear function. So the projection from in to out, basically by multiplying by matrix and adding some bias term. So we had it before. And actually, this is a simple neural network. It's a perceptron, which is simply a linear model, which is predicting to, projecting weights to, projecting inputs through weights and biases to a high dimensional vector, or the number of classes vector, okay? So now how to find the prediction y, right? I mean, we want to find what is the language of that? We don't want to just a vector. We don't want to have this vector of reals. We want, the highest one. So we are taking the argmax, okay? We're taking the maximum where this projection is at highest, right? I mean, that's what we're talking right now about. Like you pick the highest number in there, and this is going to be your answer. So sanity check. So what is this y? What is it going to be? So we have this y hat is a vector of these predictions. So these are the six values. What is going to be, if you put it through argmax, what is going to be y hat? Exactly. Thank you. It's going to be index of 1 in the one hot encoding. So it's going to be the index of the maximum here. So you can say it's 3, or it's this vector. These are equivalent because we did this mapping from categories to one hot. Okay, everybody's with me with it? Argmax is picking the index of that. Okay, which is interesting because, well, it doesn't matter. Okay, we don't have time for that. because argmax I mean, this is a discrete function. So what is argmax of vector? Like, what is, makes no sense, right? Because this is a vector. So what is argmax of the vector? Because vector is not a function. You have like argmax of a function. Yeah, so this is the value of x where the function is, you know, maximum, but a vector. So we implicitly assume we're taking this one-hot encoding thing and just taking the position of that, right? So your answer was correct, but we're misusing the notation from mathematics, like argmax on a vector is kind of, yeah, okay, sure. We take the maximum index. Okay. Great. So now I think this is important to mention, like we're talking about representations. And I think this is also, to me, was kind of sort of revealing this view. So let's dive deeper before jumping into how to make all these 6 models together into one and why this makes any sense. So what we're doing here is, while projecting this into this 6-dimensional space, we're learning some sort of representation. So first, the vector x, you know, the back of words, this is a representation of the document. We're representing a document as a, you know, the average of back of words. Great. So the dimensions is the size of the vocabulary, for example. It's very sparse and so on. So it is a mathematical representation of text. We talked about it last time. On the other hand, the vector y hat is also a representation of the document, right? Because we project it somewhere to some different space, but it's representing still the document. And this representation is, well, it has 6 dimensions, so it's more compact. And this representation of this document is more specialized for this task, right? Because we want it to be for this task, but it's still, there's some, you know, it contains some representation of the input document. Although it's kind of compressed from this, all the words into 6, you know, 6 size vector. Everybody follow? Why is that so? It's still something about a document, and we do classification on top of that, but it carries some representation. So this is okay, but also the matrix is some learned representation, actually. And the matrix here, so we learn it, right? I mean, when we run the training and do the stochastic gradient thing, we learn the parameters, the matrix. And we can have 2 views on this W matrix from either as rows or a column. So we start with the columns here. Okay, so this is the W matrix. So this is the W, and this size is the, what is this? This is the size of the vocabulary, right? So 100,000 or 10,000, and this is 6 columns, right? And we're projecting a vector through this matrix. Yes, you have a question.
The vocabulary would have words from all the languages, right?
Yes, yeah, that's a great point. I mean, I just made up something, but it should be correctly. It should have all the languages, vocabulary for all the languages, if you want to really do the task. Actually, if you really want to do the task of language identification, you wouldn't use words as units. You would use character bigrams. You know, who knows what is character bigram? What is a bigram of characters? It's exactly just 2 characters in a row. It's like AA, AB, AC. I mean, basically you cut everything into just bigram characters. And bigram characters are good features for language identification, not words, because, you know, words are different in different languages, but you have something small. Okay, but let's pretend now this is just a vocabulary, okay? And this is the matrix, and what we're doing here, we're taking the input vector and multiply by matrix and at these constants. Let's just ignore the bias now. Let's just do this, just the multiplication. So the perspective from the columns is that each of these 6 columns, and they correspond to language, like English, French, and so on, is a this dimensional vector representation of this language in terms of its characteristics, characteristic word unigram patterns, or this bigram, whatever we have as the features unigram pattern. So this is a vector representation of the language here in this learned matrix, right? And if we may, for example, cluster these vectors, we can find similar languages because they share the same sort of bigram or word unigram patterns here. So this is what we learn. We learn some representation of the language through this projection. So this is the column view. And there are any question? Yes.
I didn't understand the last sentence. How are the same words represented?
So these will be real numbers, right? So, and each of the language, the mapping to the language will kind of represent which each of the word, how each of these words is represented, or some patterns of these words in the language, in all of them.
So the numbers in each row have to be similar?
No, in each column, maybe. So if there were like very similar languages and you do a language classification task, so you would learn this representation for a language classification task, similar languages will end up with similar columns, because the words in there behave similar. They have similar kind of weights in this classification. So the learning will push them, these two languages being somewhere close. Okay, does it answer the question? Okay, cool. There is another view, and this is the row view, where each row corresponds to a, well, it's not a unigram, so it's a unigram, basically a word. A unigram, and each word provides a 6-dimensional vector representation of that word in terms of the languages it's prompting, so in this task, right? So each of these words is represented as a kind of like embeddings or embedded vector over all these 6 classes. So this is like learned representation of each word, right? It has a meaning because the word will have some projection to all these 6, to the 6 classes. Yes.
For other, would you use the average of all other?
No. We just saw, like, we just said like other is also a parameter. Yeah. So there is no distinction. It's just 6-column vector matrix, and we're just putting these classes as such. Okay. So these are 2 views. I mean, I'll give you some time to think about it later on what it really means, but we have a nice property here. So if you recall from last time, what is the average back of words? Basically, we're taking the one-hot encoding for each word in the document and sum them up and just divide by the length of the document, right? So this is what we did, like how we end up with this one-hot representation, or average back of words representation. Now, if we look back at this formula, so multiplying the input by this weights, by this matrix, and forget about the bias for now. So, and plug it here, the average back of words. So we're gonna end up with something like that. So the X basically is represented as this average back of words, and we're just plugging it here and multiplying by the matrix. So the next step we can do is, let's say, yeah, I mean, multiplication is, now maybe I'll make it wrong, but is this associative? So we can plug this, get rid of those, and plug it in here in the sum. I guess we can do that. I'm pretty sure we can do that, but I don't know if it's association or commutativity, one of those. I'm sorry. So we can do that and plug basically the multiplication here and sum over them and do this average. And what we're doing here, so this is a one-hot vector, and we're multiplying the matrix by a one-hot vector. This is effectively doing what? So we have a, let's try. We have a one-hot vector, 1, 0, 0, 1, 0, 0. And we have a matrix which is maybe 2 rows, and here will be 8, 4, 7, 6, 2, 4. It's wrong. No, 2, 3, 9, 9. So what's going to be the input? What is this multiplication doing of this matrix? Exactly. It's selecting a row. It's just selecting a row, basically, because everything, so we multiply 0 by 8 plus 1 times 4 plus 0 plus 0. And the second will be 0 times 2 plus 1 times 3. So it's 3 plus 0 and 0. So we're going to end up with the 4, 3 vector, which is exactly selecting the second row, which is exactly corresponding to the position of the 1, right? Everybody's with me? Good, because this means we're just selecting a row from this representation matrix, which corresponds to the word to the word at position, at position DI. So you're basically taking a vector from this embedding matrix and make an average of them. Well, these two things come together here. So this learned representation, this representation Y and this representation Y have two different views. One is basically saying, so this is continuous back of words representation. One is saying, we just sum word representation vectors. So this is this one we just saw in the last slide. So for each word, we're taking its row in the weight matrix and sum them up together and take an average. Or we take a back of word representation as before and multiply by this weight matrix again. And these are the same, but they give us different views. And this matrix is also called embedding matrix. So this is how we map from, let's say, sparse space or one-hot encoding to embedded to more like dense space. And we will talk about embeddings and word embeddings later on, but this is where it comes from. Like, why is it so? We have two views on these learned weights, and they tell us something about the categories and columns, also and the input tokens as rows. Yes.
For example, the example we took the 0, 1, 0. In normal situation, it has got to be a vector that has the length of the vocabularies of all languages needed, summed up, taking out the common word.
Yes. Yeah, I mean, you have large matrices. That's true. You would have like in this. Let's come back here. So, for example, if we really want to classify language here, so we would have, this would be the number of bigrams. It could be, let's say, 10,000. Okay, so it would be like 10,000 dimension vector. If we multiply if we have six languages, so this would have dimension of 10,000 rows times 6, and then the vector B would be a 6. Yeah, why not? Okay. Any other question? Oops. Okay, good. Let's move on. Now, oops, what was that? Sorry. Now, where are we? Okay, so this is like what these embeddings are, what the projection is, and I think it gives interesting view on the embeddings. What is it like? What is learned in this representation? So representation learning is central to deep learning. So the main power of deep learning is basically the ability to learn good representation. So all these projection matrices are learned and they give us great representation. But let's come back to the task we had before. So, okay, we have this multidimensional linear transformation. So we're projecting from one space to another, maybe from 10,000 to 6, but we want to turn it into probabilities for some reason, because we want to kind of find the best prediction from these number of classes. For example, what is the language, and we want to give it a probability because we had in the sigmoid, in the logistic regression, we had in the binary logistic regression, we had this probability of being 1 or probability of being 2. Maybe you want to put probabilities of these predictions on these multi-class classification as well. So we want to turn output vector into probabilities of these different classes, right? So remember, we have this vector, this y hat vector would be this 6 numbers, and we want to do something better. So let's quick recap. What is categorical probability distribution? So everybody had a background in probability theory a little bit. Who hasn't heard of categorical distribution or probability distribution at all? Great. So we have a random variable, which is defined over k categories. And these categories are distinct and there's no ordering and so on. And these are mapped to typically natural numbers, so 1, 2, up to k categories. So for example, in our categorical distribution, we would have English would be 1 and German 2 and so on, so on, so on. And then each category is parameterized with probability of this category. So for example, the probability of X being English would be, I don't know, some probability like 0.1, and the probability of X being 2 could be 0.4, and so on. So we're saying which, of these different choices, what is the probability of each of them. And there is one thing that the categorical probability distribution has to take into account. I mean, these have to be positive, obviously, as probabilities between 0 and 1. And there must be one constraint on this whole thing, which is, if this is a probability distribution, there's one condition or one definition, sort of. Yes. They have to sum up to 1, exactly. So all of them sum up to 1. Okay. So basically, then if we had a vector over our 6 categories, 1, 2, 3, 4, 5, 6, then it has to sum up to 1 to be a probability distribution over these categories. Okay. So I just want to bring this, terminology a little bit here, but I guess this is clear case. The question here is that how to turn a vector, unbounded vector in this, let's say, 6-dimensional space into categorical probability distribution. So now the question is, we have again R6, which is a vector, and each of them could be from -∞ to +∞. How to turn it into a categorical probability distribution? Any ideas? You first. Oh, okay, using the softmax. You know the answer already. Okay, good. So I want to try like something super naive, but if you know the softmax, this is the solution, right? Yeah. Any other? Okay, so anyone who hasn't heard of softmax but has an idea, like creative, like how to turn this vector into probability distribution?
We could add up all the values and then divide each one by the.
Okay, you would say you would sum up all these values, and then basically normalizing each value by this sum.
Yeah. This
is great. There's a catch. What is a catch if you do that? Negative numbers. Yeah, it will break negative numbers. Okay, so you hate negative numbers.
Take the absolute value.
You could take an absolute value and divide it by the sum of that. And I think it will work, actually. I think it must work. Because you take, let's say, this, put it into absolute value, so xi absolute value over sum of j xj. Okay, good. I think it's actually, it will be sufficient to do so.
But you would lose the minus, right?
You would lose the minus, right? You would, exactly. It's bad.
Yeah.
It's the opposite, yes. So basically, you would lose half of the information you would have in the value, right? Okay, so we need something else. But this is, this is a great progress, because this, we need to make it, okay, so the catch here, how to make any number positive number. So we're simplifying the question here. How to make any number, how to turn something from -∞ to +∞ into 0 to infinity. Yes.
You just use the lowest number as the starting point, set it at 0, and then.
Yeah, you can set a baseline, but it's just arbitrary because it depends on the values.
So I mean, like, take the lowest number from the vector, like if there's a -10, let the lowest number say, okay, we add 10.
Yeah, exactly. You can put it, you can put a sort of a bias in a way, like a threshold, and then just add up. But it's depending on the values, and you want to do it a function like values independent.
Oh.
Any other idea how to turn this into? You can put a power value like xy squared.
These two were for the power of the number that we have here.
Oh, 2 to x. Yes, I think you're on a good way. It should, yeah, exactly. You can do that. Yeah, and maybe we're not gonna use 2 to power x, but we might use something different, which is nicely differentiable. So 2 power x is great. Anything else we can use instead of 2 power x, which is nice derivatives. E power x, exactly. Yeah, we're getting somewhere. Okay. So this is great. This gives us positive numbers, this is even greater because it gives us differentiation, which is just the same function. And what we end up here now, so if we replace this absolute values with these e to x, we found a softmax. Congratulations, great job. No, I mean, come on. I mean, you can think about it like, there's a reason why softmax looks like the softmax. If I should just show you the equation, like, okay, whatever. But if you come up to the idea like how to build it, yeah, then it has a meaning, right? So we're putting everything. It's a nonlinear bijection from minus infinity to infinity to plus here. So this is the exponentiation denominator, and the denominator is just normalization constant. This is great. Okay, so what is missing on the picture here? So we have a softmax, which kind of creates a probability distribution. This gives us a probability distribution over any real vector. This is important, by the way, to remember. I mean, you should know softmax. If you leave deep learning for NLP and come to someone, it's like, I don't remember softmax, but I can look it up on Wikipedia. No, I'm sorry. You should, I mean, this is easy, but you should know that. What's missing here for us? Because we want to plug the softmax somewhere later on. What is missing on the picture? We need to do something with the softmax. As with any other function, we're plugging into our functions, into our composite functions.
Derivative.
Yeah, we need the derivative, exactly. You need the derivative for each of these positions to the arguments. And actually, I didn't look. I don't know. I mean, take it as a homework, because the Wikipedia solution was kind of ugly, and I hadn't time like to do it by hand. So there is a derivative, obviously, of this function with respect to each argument, but it wasn't like this. It didn't look straightforward just to put it here on Wikipedia. So maybe you wanna try it by your hand, but there's a derivative, obviously. Okay. Great. So we have this softmax function. What else? Yeah. So softmax, actually, we typically use softmax in different setup, also with this thing called temperature T. And if you ever play with ChatGPT or some APIs from ChatGPT or GPT-4, there's a parameter called temperature. Have you seen that before? Anybody heard of temperature? You know why it's temperature? Because of this. It's just basically it's putting, and this is coming from physics, as far as I know, because it has some meaning on the entropy of the universe or whatever. But it's basically dividing each of these constant by this temperature. And the meaning of that is that, for example, the input of softmax would be 301. And if we use no temperature, the output of the softmax is going to be like that. So this is a probability distribution. Everything is between 0 and 1. And as we see, 3 will be the biggest, 0 will be somewhere low, but not 0, and 1 will be somewhere low, but not, not as big as that. If we use like high temperature, this is getting more uniform, right? And why is it in ChatGPT? Because you can put temperature on the sampling basically of the next word, something like that. So high temperature means more randomness in the sampling of the next word, while low temperature means basically almost certainty in the distribution. Okay, so the temperature is just a parameter which kind of has an influence on the output of the softmax. Okay, any question? Great. So we have a softmax, great. We're gonna plug the softmax somewhere, that's for sure. But we had a loss function for the sigmoid. So the loss function, what was the name again? Binary cross-entropy, right? Was a loss function, was these two logarithms and things like that. But what are we gonna do for the softmax? Well, we're gonna use a categorical cross-entropy, also known as negative log likelihood. Remember this, please. This is like central to machine learning and negative log likelihood. What you're doing? Yeah, I'm minimizing negative log likelihood. Okay, good. What does it mean? Yeah, so it's a categorical cross-entropy. Okay, what does it mean? So this is it. Basically, we have again. So what we have, the y vector is the vector of the distribution of the classes labels, and now we have two options. So we would have, this would be basically a one-hot encoding. So 0, 0, 1, 0, 0, 0, would be like the hard decision, you know, but you would say like maybe you want to like a distribution of languages, so it could be anything actually. I mean, we can have like it could be 0.5 German and 0.5 English, and the rest will be zeros. Maybe. Why not? I mean, as long as this is probability distribution, we're fine. But typically we use like one hot label. Sorry, one hot encoding for the labels. And the output of softmax, as we just saw, will be something like something like this. So maybe this would be output of the softmax. So some distribution which sums up to 1. What we are trying to do is to make this difference of these two distributions as small as possible. Okay, so this is a probability distribution, very spiky here. This is a probability distribution, and we want to make this distribution difference as small as possible. Why? Because we want the model to predict what is in the gold standard data. How to do that? We're using this negative log likelihood or cross-entropy loss, which has this very nice formula or very ugly formula depending on perspective. And it's so it's basically iterating over all these categories and computing log of one multiplying by the value of the other. And so why is this so? Where is this coming from? I mean, maybe you could remember this one. Yeah, I guess you can remember that. But why is this? Where is this coming from? I mean, why is this so? Like minus logarithms from one the other. There's a meaning. So typically you will find this as learn it, and this is a cross entropy loss. If you think about it, we want to find a distance between two distributions, right? So how do you find distance or differences between two distributions? Anybody who has probability theory, how do you compare two distributions? Is there a way, if you have like one distribution and another distribution over the same values, can you measure the difference between two distributions? Is there a way? Exactly KL? Divergence. KL divergence or divergence? Yes, so KL divergence. Okay, good. How do you compute KL divergence? Anybody knows how to compute KL divergence? It's been a while, I know, I'm sorry, yes. But if you go to KL divergence, it's an expectation over a function of one variable, and there's some logarithm in there, and it's like, oh, it looks similar. Okay, yes, because this is coming from the KL divergence. So this is optional slide. I don't want to scare you off, because I scared off last year everybody here, so I'm not going to go through this. But this is the KL divergence over two probabilities over the same random variable with the same range. And this is as an expectation of the py, and here's the function of the random variable, which is qy. Okay, so yeah, this is the definition of KL divergence. And then if you do the math and logarithms and blah 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 blah, you end up with two things. You can decompose this into two things. Okay, what is this? Anyone knows this from probability theory? What is H typically? So this is the entropy. So you compose this KL divergence into entropy of y, and this is expectation of the other thing. And if you do the math here and make this explicit the expectation here, you end up with this formula. This is exactly coming from there. So basically, you want to compare two distributions. You use KL divergence. You decompose KL divergence into two parts, and one part doesn't really depend on the predictions, so you just get rid of it because you cannot optimize it, and take the part you need to optimize. And this is going to be cross entropy. Okay. So there's a reason why this looks like how it looks like, but you can also like remember just the formula. If you do it for if k is 2, you will end up with surprise, 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 surprise. Oh, Jesus, it's long. You will end up with this. So this is the cross entropy for two variables. We don't use sum here, but it's the same thing. Just spit out exactly. Okay. It's coming from the KL divergence. Oops, that was too slow, too fast. Okay, and I think we'll actually finish today, maybe, hopefully. So this is like optional slide, but that like it's coming from somewhere. There's a meaning. So we had this linear functions. Okay, I'm sorry. I need just 6 minutes and we're through it. Is okay? Cool. Good. So now it's going to be fun. We have the linear layer. We put a softmax on top of that. Did we do that? I guess so. No, the softmax will give you probability distribution of all these outputs of these linear transformation. Linear transformation, 6 size vector, softmax, turn it into probability distribution. And you pick the maximum. Or you know the probability of each class from their predictions. The whole fun of deep learning is that you can stack things together. So what you can do is, well, this looks ugly, right? But it's not. Stay with me. So we have again our input vector and the weights, and this is the linear transformation. So we have one linear transformation as we had before. What if we take this and do another transformation here with another set of parameters, and then compute the loss and make a predictions, right? So we would basically inline this would be the first linear function into another linear transformation. And we have more dimensions here. So this is the input dimension. There will be the output dimension. And of course, to make this multiplication work, we have this matrices and biases vectors. D1 is the dimensionality of the first function, and then there's the other function, right? So can we do that? We could be stacking things together and being, having more projections, basically. So we would basically project our high-dimensional space into another space, and then we can project from this space to yet another space with the hope that we will end up with a great representation of the problem, that the classification will be easy. There is one catch with that. I mean, so first question is, are you with me on this? We can stack things together and have some linear functions on top of each other. Does it make sense? Right? So, and the dimensions have meaning, is there? I mean, meaning in terms of they have to match. So this is great, but what happens if you do linear transformation after another linear transformation? What do you end up with? What will be the output function?
Then you can basically put them together and you get one linear transformation.
Exactly. If you do linear transformation one after each other, you will end up with one linear transformation in total. So it will still be linear. So it won't solve the problem of nonlinearity in the data. I don't think did we talk about nonlinearity in the data or not? I don't think so. Okay, we should address that. Yeah, sorry. It's a glitch in the screenplay as well. But the idea is that, okay, we can stack them together. And in order to learn better representation, not just linear representations, what is a linear representation? You're just projecting something on maybe like on a wall in 2D. But all the distances will be still the same. But we want to learn better representation, which kind of tears, maybe the dimensions apart or the instances apart. So the trick here is that we add a nonlinearity in here. So we take the output of the first, let's call it layer. Why not? Because it is a layer. And push it through some nonlinear function, and then the rest is the same as before. Yes.
Where's the y?
Where's the y?
What is the y? X is the input.
Yes. And y is the label.
Oh, okay.
Yeah. So this is the same setup. We have a input, and this is the gold label. Gold label, as we had before, but this is in between. The transformation is getting more complicated. Here it was just two linear transformation on top of each other, but they don't give any added value because it will be still linear, like two matrices after each other. But here we're adding some nonlinear function in there, which we typically call also a activation function. And it's doing some nested things in the space. So you project somewhere and push it through some nonlinearity, which will do some weird things in this space. So everybody's with me on that? Yes. Yes. Mm-hmm. Yes.
shouldn't it be D1 because the
Yes, I guess this is correct. This should be D1 exactly. Thank you very much. Yeah, great catch. Great catch. Thanks a lot. Yes. I copy pasted it and then, yes. Yeah, that's correct. Exactly. Well, let's come back here. So this I have to fix. But we're plugging the activation here, and the activation definitely will be yes. I mean, now the dimensions are correct, so it will be applied to a vector of this dimension, and the vector comes out. So we're not doing any transformation here. We just apply this on each element of this transformation of this this vector coming out of this layer. Okay. Any questions? Good. So what is this nonlinear function could be? What is a nonlinear function? If you say ReLU, don't say it. If you say something else, say it. 10H. Yes. Okay. Well, we already had a nonlinear function before. 10H is great. So 10 tangus hypergolicus, which maps everything into, oh, how's that? Maybe like that. So between minus 0.5 and 0.5, is it correct? I hope so. Is it -1 to 1? Yeah, okay. No. Let's make it right. So -1 and 1. And we had another one. We had something very similar, almost very similar. We had a sigmoid, exactly. Yeah. So it could be a sigmoid, which maps everything basically. And this is, as I said, this is here's what's coming out of here is a vector, and we applying this on each element independently, right? So we can use 10H, we can use sigmoid. They used to be popular. We have something else. You were saying? No, you were saying ReLU. ReLU. Okay, we have ReLU. So we have ReLU, which is very weird actual activation function because it's saying just, everything which is positive will stay the same, right? It will be like the input will be the output if this is a positive number, and if it's negative, it will be just 0. So basically, we're kind of like breaking the function in the middle and saying, or you can say like it will be maximum of the input or the 0. So okay, this is great. What do we need to compute for this thing? I mean, everything has to be. We need for every function we plug into the network. We need what? We need derivative. So what's going to be derivative of ReLU? 0 and 1? Yeah, exactly. So the derivative here will be 0, and here the derivative will be 1. It's beautiful.
Like we have this thing at the 0 point. So
and this is a catch. Yes. What's this? It's not continuous. Yeah, you cannot derivative. Exactly. So what you're saying is that's why we don't need to have continuous functions, because this is not this is not continuous in a way like it's differentiable at every point, because here we're kind of breaking it. So we arbitrarily choose saying like at 0 it's going to be 1 or 0, just by definition. We don't care about it because the chances it will be exactly 0 is super low. But if so, you can say let's the derivative be 1 or 0. Yeah, like a design choice. You say in my implementation I'm going to use derivative of 1 for everything which is greater or equal to 0. It doesn't affect that much. Exactly. And this is the ReLU. ReLU is like one of the most widely used nonlinearities in deep learning and natural language processing so far. So it has nice derivatives, nice implementation. It's very fast because it's just the identity function, or just basically one-liner. So it's super fast as well to compute. And we're going to plug it on many places. Any question? Great, we're through. Made it. So, okay, binary classification as linear function word sigmoids. Yeah, we hit it. So cross-entropy logistic loss, important to remember. Then mini-batch SGD is very important. Actually, everything is important except for the Kyle divergence. But if you want to sound smart in a bar, you can learn it as well. And then we have the stacking and multi-layer perceptron. Okay, thanks a lot. See you in a week.